Hello, this is Jeff Moreau here with Atlas Moreau and Dr. Robert Moreau, and we've been talking a little bit about fluid dynamics in my regular physics classes. And while we're looking at different applications, I have my students looking at a video about fluidized airbeds. And Dad, what did you think of that video?
I thought it was very good. It looked like I wanted to get one of those hot tubs full of sand and jump in.
But to give us a better introduction about why I have you on the call here, can you introduce yourself, tell us what you were doing with your main profession for 38 years?
Yes, I worked for the United States Department of Agriculture for 38 years, and I was a research chemist. My PhD is in biochemistry, and what I ended up doing for most of those years is food chemistry and food analytical chemistry, and worked all of that time in Philadelphia and enjoyed my work. Worked with mainly with analytical instruments, analyzing different components in foods. Most of them were vegetable oils, fats and oils, things like corn oil, soybean oil, different types of salad oil.
Gotcha. Thank you. And just out of curiosity, when did you first become aware of the concept of fluidized airbeds?
Actually, about 15 years ago, we hired a new chemist, actually a chemical engineer, who was actually originally from Ghana, and he was an expert on fluidized beds. And at that time, we were looking at new ways to make biofuels to replace petroleum fuels as a green alternative to petroleum. And this Dr. Boateng, who worked with me, had developed a method called fast pyrolysis, which is heating compounds or heating carbon in the absence of oxygen, breaks them down. It's like combustion minus the oxygen. So he developed a fluidized bed reactor to be able to break down woody biomass like sawdust, grass, agricultural waste, and convert it into biofuels.
Thank you. So 15 years ago, you first learned of it. And then you brought that guy on for his uses of it and for his expertise in it. Is there more you'd have to say about how exactly it was then used in your work or in things that you were working with?
Well, he hired two other scientists, and that team, I worked with that team. Actually, I supervised them for the last 5 years, and they started out making a small reactor that could react a couple ounces or half a pound of material. Then they built a bigger one that could react about 20 pounds a day. And then about 5 years ago, they received a big $8 million grant, and they made a reactor that you could pull in a trailer that would react about 2 tons per day of woody biomass. And it contained, each of these contained progressively larger fluidized beds. And the reason that they used fluidized beds is that in order to do, with fast pyrolysis, convert most of the solid biomass into liquid biofuel, which is what you want. If you heat it, fast pyrolysis means very rapid, like within milliseconds from the time you heat the material, you break it down into a liquid. If you do it too slow or too fast, you break it down either into a solid like charcoal. Charcoal is really a biomass that has been heated change it into a charcoal briquette. You can also, if you react it longer, you can break it down into gases. So this fast pyrolysis is kind of a happy medium where the amount of time that it's heated is right to give you mostly liquids. And before you introduce the biomass into this fluidized bed, you need to grind the particles into very small pieces, about 1 millimeter or less pieces, so that they, within milliseconds of the time that they come in contact with the fluidized bed, the heat breaks them down from a solid into a liquid.
So they were using, similar to the video that I shared with you, in this machine that was making a biofuel out of wheatgrass?
Well, one of the feedstocks they use is called switchgrass.
Switchgrass, right.
It's a fast-growing prairie grass.
In this machine, part of the filtration process involved this fluidized bed with a certain type of sand that had air running beneath it, correct?
Correct. Actually, it was fairly common sand.
Okay.
But it was nitrogen. There was no oxygen in the air that was used, because we didn't want to get combustion to CO2. We wanted to get pyrolysis. So you need an inert gas like nitrogen. You can use other gases. You just can't have any oxygen.
Gotcha. Just a couple more questions for you here. Let's see if Atlas has any questions then. But I was just curious, if we're talking about fluid dynamics here, with all your years of work, and you just retired, was it last year or the year before?
Last June, 10 months ago.
So just retired last year, but in all the years prior to that, do you have any interesting stories to share about unusual properties of fluids, or how things like that impacted your experiments?
I do. Actually, the fluidized bed work is work that I was kind of secondarily involved in. But about 20 years ago, I started using a fluid called supercritical fluid. And actually, I just happened to have a graph here for your students. And you've studied the different stages or states that matter can be in. It can be a solid, it can be a liquid, it can be a gas, or in unusual circumstances, you can have plasma. But actually, there's a fifth state that isn't mentioned often, and it's called supercritical fluids. And this graph shows it. If you raise the pressure of matter high enough, you can get to the point where the line between the gas phase and the liquid phase is kind of blurred. And the supercritical fluid has some of the properties of a liquid in that it flows, but it has some of the properties of a gas in that it can penetrate into small openings. So the technology that we used was called supercritical carbon dioxide extraction. And what we would do is to purchase a cylinder of carbon dioxide, and we had an extractor which would increase the pressure up to this point. We'd increase the pressure and the temperature up to the point where we had supercritical carbon dioxide in the supercritical fluid form. And what we could do with that is to use it to get vegetable oils. It was kind of a way to a green technology to be able to remove vegetable oils from things like corn and soybeans and other ways to get vegetable oils in a way that produced an oil that was safer. And once you extract it, it's very easy to remove. You just bring it down to atmospheric pressure and the CO2 dissipates off, and you end up with a very clean oil. So that's, that's my main experience. I had an extractor, and we could extract up to 1 kilogram of material within an hour and obtain fluid that way. One of the neat applications for this supercritical CO2 extraction is it's one of the cleanest ways to decaffeinate coffee.
To decaffeinate coffee.
To remove the caffeine from coffee, yes.
So when I go to buy a bag of coffee beans, if it says water processed, is that the same? Is that a different way of doing it? Because I'll see that on bags of decaf coffee. It'll say water processed.
Sometimes when it's water processed, sometimes it includes the CO2, and so there's a method that uses it and a method that doesn't.
Gotcha.
But they're both safer than some of the alternatives.
Got it. By the way, I don't know if you saw a second ago, but if you're talking about your different vegetables and stuff with that, he's got his carrot here. I believe he's got his radish there. Onion? I'm not sure actually. But anyway, our final question before we let you go and we take care of this little man. You worked with fluids. I know that wasn't your primary thing, but you worked with fluids in part of the filtration stuff and everything. We've been talking with my students about all sorts of different applications and principles. And would you say you have a favorite property of fluid dynamics, of fluids, of what's one of your favorite applications or things just in general? Mine's Bernoulli's. I think Bernoulli's principle just has a ton of fun, weird applications to it. Do you have any favorites?
I like swimming.
Swimming. You do like swimming. So buoyancy, Archimedes' principle, all that stuff would be stuff that you would then gravitate towards. Well, thank you for your time. We're very appreciative that we could get you amidst this self-quarantine. You are drooling all over the place. And thank you for being part of this and for answering our questions here.
You're welcome. If you have any other questions, Atlas has been listening very attentively, so he probably could tell you the answer, but if not, give me a call.
Perfect. Thank you. Well, I'm going to end this here, and I appreciate your time and help with that. I will just say the other cameo he's got his celestial buddies. We've got our Earth. He's been eating the sun over there, Pluto and Sharon. But anyway, I will end this meeting and take care of the little boy. But thank you again. See you later, Dad.
You're welcome. Goodbye.